Hi, Kelvin here. In this video, we are going to consider this simply supported beam. A simply supported beam is a beam supported at both ends only. And for the beam, I will show you how to calculate the reaction forces. Then we are going to draw the shear force diagram. And finally, we are going to draw the bending moment diagram. Consider a structural frame. In this video, we are going to assume that this is the support for this beam. I will just ignore these two supports here, and I will assume there is a force at this point and this point of this beam. The first step towards solving this problem is step number 1. We are going to draw the free body diagram. The free body diagram is simply redrawing the question, but we are going to replace the support. Here we have a pinned support, and for a pinned support, it's going to be two arrows, a vertical arrow and a horizontal arrow. The vertical arrow, I can call it V subscript A, and this I can call it H subscript A. At times you can use R subscript A. And for the roller, it's going to just be only one arrow, and I can call this V subscript D, or I can use R subscript D. Now that we have the free body diagram, step number 2. In step 2, we're going to have that all the forces going up must be equal to all the forces coming down on the beam. V subscript A, and that's a plus V subscript D, are all going up. Then for the forces coming down, 40 and 80 are all coming down. And we're going to have that the forces going up will be equal to 120 kilonewton. Next, let's consider step 3. In step 3, we are going to say that the forces going to the right must be equal to the forces going to the left. H subscript A is going towards the right, and no force is coming towards the left, so it is 0. Now we have obtained one of the answers, because I'm looking for these 3 forces. Next, step 4. In step number 4, we are going to say that the summation of all the moments acting at a point, it can be point A, B, C, or D. But here we are going to say for point A is equal to 0 mathematically. But the meaning of this is that the clockwise moment must be equal to the anti-clockwise moment. That is, I'm going to take a reference at this point A, and I will assume that all the forces acting at this point is 0. Now I'm left with 40 kilonewton, 80 kilonewton, and V subscript D to analyze. I'm going to consider this each at a time. Let me consider 40 kilonewton. I will assume that 80 and V subscript D does not exist, that only 40 is acting on this beam. This 40 will push this beam down to turn around this point in the clockwise direction. So I'm going to have 40 multiplied by the distance from this 40 to this point is 2. This is moment. Force multiplied by perpendicular distance is moment. It must be perpendicular. Force multiplied by distance is not moment if it is not perpendicular. I'm done with 40. Next, let me consider 80. I will say plus. I will assume this time around that 40 and V subscript D does not exist. What will 80 do to this beam if it pushes it down to turn around this point? It's going to push it down to fail in the clockwise direction. Hence, I'm going to have 80 multiply the distance from 80 to where we are taking our reference from is 2 plus 2, which is 4. I'm done with 40. I'm done with 80. Remaining V subscript D. I will assume that 40 and 80 does not exist. Hence, this V subscript D force will push this beam up to turn in the anti-clockwise direction. Hence, I will consider the other side. V subscript D will multiply the perpendicular distance to where we are taking moment from is 2 plus 2 plus 2, which is 6. Next, this will give you 80. This will give you 320. And here we have 6 V subscript D. Next, here we have 400. I want this 6 to leave here, and on the other side it will divide, leaving V subscript D isolated on the other side. And VD will give us 66.67 kilonewton. Now we have found the value of V subscript D. Next, let's look for the final reaction force, V subscript A. Next, step 5. We are going to substitute this value, which is V subscript D, into step 2. In step 2, we have that V subscript A plus V subscript D is 120. V subscript A will give us 120 minus, we have here 66.67. And V subscript A will now give us 53.33 kilonewton. Now we have found the value of our V subscript A. We have this value now, we have this value, and we have this value. With this replacement, we can now draw the shear force diagram and the bending moment diagram for this simply supported beam. In replacing these reaction forces, I can ignore H subscript A because it is 0. Also, if you add all the forces going up, it's going to give you the addition of all the forces coming down, which is 120. Next, we're going to draw a straight line here after replacing the values of our reaction forces. Next, I will draw a line for the shear force, then I will draw another line for the bending moment diagram. So this is for the shear force diagram, and this is for the bending moment diagram. If this is A, this will also be A. Remember, this is the zero shear force line, and this is the zero bending moment line. And this is B. This will also be B. This is C, and this will also be C. This is D, and this will also be D. Next, for the shear force diagram, we're going to start from 0, and this will push up 53.33. So we are moving up to 53.33. We are assuming that here is, I'm not using a graph, so this is our assumption here. Next, because there is no uniformly distributed load here, this will be a straight line, and it will stop at B. Next, at point B, 40, we push it down. Now, if we have 53.33 minus 40, that means at this point, I'm going to have 13.33. Next, between B and C, there is no load. Hence, I will draw a straight line to C. This is a straight line, and here is also 13.33 at this point, still on the same horizontal line. Remember, this is 53.33, this position. Also this point. Next, at this point, 80, we push it down to 13.33. However, 80 minus 13.33 will give you 66.67. Remember, this part is the positive shear force, and anything below is the negative shear force. This side is a positive bending, anything below is a negative. This is our convention for this drawing. Hence, at this point, we are going to have 66.67 with a minus because it's on the negative side. Next, at this point, no uniformly distributed load, there is no load. Hence, we are going to draw a straight line to point D. Now we are here. At point D, this is 66.67. The minus is just indicating where it is on this diagram. 66.67, we push this back to 0. And this is our shear force diagram. Next, this is positive, and this is negative. Next, to draw our bending moment diagram, there are two methods we can use. The first method is the mathematical method. In the mathematical method, I will cut this beam here at 40 to know the bending moment value at point B. I will cut it and I will represent this value like this, 40 here. This is 2 meters. I want to know the value of the bending moment at this point B. I will also do the same for point C. I want to know what happens when 80 kilonewton comes down here. This point is 40. This is point A and this is A. This is B. So I will do this to know the bending at B and also to know the bending moment value at point C. This is using the mathematical method. I'm not going to use this in this video. I will use this in another video. But in this video, I'm going to use the second method, which is the graphical method. In the graphical method, I'm going to say that the area under the bending moment diagram is the value of the bending moment. So I'm going to use this by finding the area of this, the area of this, and the area of this. If you use the mathematical method, you will still get the value we're looking for here. Likewise, if you use the graphical method, you are going to still find the value. Both will give you the same answer. Next, let us find the area of this shaded portion, which is just only here. The area of this is length times the breadth, or length times the width. From A to B is 2 meters. From B to C is 2 meters. And from C to D is 2 meters. Hence, we're going to have 2 meters multiplied by 53.33 kilonewton. And we're going to have 106.66 kilonewton meters. Let's assume that this is the point, which is 106.66. This is our assumption. And this point is 0. At the end of a beam, the bending moment is 0. At this end and at this end. Hence, this end is 0. And this end of D should also be 0. Maximum bending moment occurs at the midspan of a beam. Maximum shear occurs at the support. Always remember this. Next, we want to look for the area of this portion. And the area here will give us 2 meters times the length is 13.33. And for this area, we're going to have 26.66 kilonewton meters. We're going to add this to this. Next, we're going to add the value of this area. Remember, it was 0 plus this that gave us this. Now, we're going to add this to the new value. The new value of this addition will give us 133.32 kilonewton meters, which is a point above this value, not to scale. Hence, this new point is 133.32. Next, we're going to find the value of this area. This area is 2 meters, and this length is a negative of minus 66.67. Remember, this is kilonewton. If you multiply these two by this, you're going to have 133 0.34 kilonewton meters. Now, this new value we add to this value. However, there is a minus here. Hence, this becomes minus 133.34 because this is a minus downwards. Remember, this is our first value, our second value for the bending moment, and this is our third value. The fourth value will be this plus this. However, this will minus because of this minus, and you will end up having minus 0.02 when this subtracts this. In structural analysis, this value of plus or minus this value is usually ignored. I didn't mean we had a value of plus or minus 0.05. This tolerance is the maximum we can accept. Hence, we can ignore this and approximate it to 0. Hence, our next point will be at D. Next, there is no uniformly distributed load on this beam. For beams with uniformly distributed load, including cantilever beams, check out the videos in the playlist. Next, I will join this point with a straight line. Here, we are not going to have a curve. We have a curve if there is uniformly distributed load. Here, there is no parabolic shape. With a straight line, I will join this, I will join this, then I will join this down. This becomes my bending moment diagram. And because it's on this positive side of the diagram, this becomes a plus. And this becomes the shear force diagram, and this is the bending moment diagram for this simply supported beam. I use the graphical method here. You can also watch the video for the mathematical method. Both will give us the same shape for the shear force diagram and for the bending moment diagram. If you find this video helpful, feel free to click the like button and subscribe for more videos like this. I will see you in the next video lesson.